Right. So we are at 3:22. So we're going to go ahead and start the last session of the theoretical aspects of trustworthy AI Simons Institute workshop. I have the pleasure of introducing Shahin. He's visiting us from Drexel University and will be speaking about robust algorithmic recourse with predictions. So, without further ado, Shahin.
Yeah, thanks for the introduction. And thank you for inviting me for such a fun workshop that bring together so many people from a wide range of backgrounds. It was very fun. And thank you everyone who is here. I know this workshop has been going on for 5 days and it's a Friday afternoon. And most of you are looking forward to go back to see your family. So thanks for sticking around till the last talk. So today I'm going to talk about robust algorithmic recourse with predictions. This is joint work with my student Shitij and my colleague Vasilis. So most of what I'm going to talk about is joint work with these two people. Towards the end, I talk about a couple of other ongoing works, and I tell you who are the other people who are my collaborators. So I generally work in the field of responsible computing. So we use algorithms in many high-impact settings. Some examples of this are lending, hiring, and sentencing. And over the past 20 years, we are kind of, not slowly, but realizing that accuracy by itself is not sufficient. So we want these algorithms to satisfy some other properties. I'm going to list a few of these properties here, mainly based on the timeline that we started caring about these properties. So one of them is privacy. I think the gold standard notion of privacy that people use nowadays is differential privacy. So here, in the context of these applications, if we train a machine learning model in any of these settings, we want our trained model to not leak any information about the people whose data are used to train this model. Fairness is another topic. So there are many different definitions of fairness, trying to basically avoid disparate treatment or disparate impact. There is really no right or wrong definition of fairness. And we have a good understanding, at least for basic settings like classifications, that what are the relationship between these notions of fairness and what are the incompatibilities. We obviously care about robustness. So in any of these domains, we expect robustness based with respect to the input and with respect to the parameters of the model. So if two people that are similar, roughly going through the same decision-making system, we want similar decisions to be made for them. And at the same time, if we have two models that are roughly similar, we want these two models to make roughly the same decision for a specific individual. We care about explainability and interpretability. So Pratik was talking about these topics in the previous part. And generally, we want to study these topics not by themselves, but we want to kind of think about how they interact with each other. Because if we have a system that is trustworthy, it's going to satisfy many of these properties, if not all of them at the same time. OK, so today I'm going to talk about algorithmic recourse, which is one other property that generally falls within counterfactual explanation. So let me just briefly tell you what it is through an example. So suppose you have a person who went to a bank and they got denied for a loan. So that person, to have the trust in the system, they want the bank model to be fair, maybe have some certificate of fairness. They want the bank to be able to explain why they get rejected. But at the end of the day, what they really would be useful with this person is they want to know a pathway to get accepted. So algorithmic recourse exactly deal with this problem. So here is an example of a hypothetical applicant who went to the bank. And these are some of the initial features of this applicant, for example, number of credit cards and how much debt this person has. And the recourse solution basically gives this person a bunch of suggestions saying which one of your features you need to change and by how much. So for example, here, the person has too many credit cards. So the solution wants it to lower the credit cards and lower the debt and some other additional things. So we want to think about how to generate these counterfactual explanations that has some other nice properties. Yes.
So is this uniquely defined, or there are many possible recourses that could be there?
You'll see in a second.
Okay.
Yeah, it's a good question. So let me formalize the setting that I'm going to work with. So here we have a classifier. So this classifier, for now, I'm just assuming it maps the inputs to 0 and 1. I have an input that if I pass the input to the classifier will say 0. So that's the person who got rejected. And I have a cost function that basically tells me how to, what is the cost of modifying every instance to any other instance. So I'm going to talk about each of these aspects in a second, but just given this very general frameworks of how we define cost functions and functions, what I care about is I want to, if I start from x0, I want to find an x that is close to x0, that is close as possible in terms of my cost function, and has the property that f of x is 1. So just to give you some visualization, if I have a linear model and I'm looking at L2 distances as my cost function, this is basically the shortest path I have to the boundary of that linear model. And the solution here might not be unique, especially if I have models that are more complex. So there is no single best solution. And I don't quite cover, but you might prefer situations where you have a slightly suboptimal solution, but that solution is more sparse. So you don't have to change a lot of your features. So I'm going to start with talking about the relaxation of this problem. So this is the exact version that you want to find a point that exactly give you the label 1. So a slight relaxation is now I'm going to assume my classifier is probabilistic. So instead of giving me 0, 1, it gives me a probability that the outcome is going to be 1, which is the desired outcome. So now I can write this formulation as a relaxation. It has 2 terms. So again, I care about the cost of transforming x0 to x. But now I might not exactly want f of x to be 1. Remember, f of x is probabilistic, so it maps a number between 0 and 1. I want that number to be as close to 1, and I'm going to penalize how far is it from 1 by some loss function. And I'm basically looking at a combination of these 2 factors, and lambda balances them out. So if lambda is a very small number, that means I mainly care about finding a data point that has label as close as possible to 1, no matter how much is the cost. If lambda is larger, I somehow care about the cost of transformation. So throughout, when I'm going to talk about cost, I'm going to talk about this term. And when I talk about validity, it's sort of the inverse of these terms, because this is invalidity of the recourse, so how much I'm getting penalized if the label is not 1. So validity is, you can think about kind of an inverse quantity. I'm not going to define it formally. And if you have a choice of whether you're going to work with the exact solution or the relaxed formulation or exact formulation, what cost function you're going to use, what model you're going to use, and how much information you have, you get a different optimization problem. And this is just maybe the 5 initial work that kind of worked on different aspects. So I give you some examples. So people have thought about a situation that the model is linear versus a situation that model is more general but differentiable. Cost function, you can work with LP norms. So that is something that I'm going to focus for the most part today. So the problem with LP norms as a cost function is you're assuming that features are uncorrelated, and you can change each of the features independently. So this is an assumption that is not satisfied in practice. So there are works that kind of studying the causal relationship between the features. I'm here assuming that I know the model and I know the cost function, but in practice, it's really hard to know, especially what the cost function is, because you might not know exactly how much does it cost you to change your features from this, but you might be able to give feedback in terms of pairwise comparison. So if I tell you, hey, here are 2 solutions, x1 and x2, which one do you think is easier for you? You might be able to tell me which one, and based on some of these, I can try to fit a cost function to your preferences. And I might not have access to the model either. I might have only black box access to the model. So I might not know what the model is. But for the most part that I'm going to talk about today, all of these things are known, and I'm going to make simplifying assumption on all of them because my goal is that we want to kind of design an optimal algorithm. Okay. So there are many problems with the formulation that I discussed in the previous slides. I'm going to talk about a few of them today. So one kind of problem is implementing recourse is often time-consuming. And in practice, model often gets updated periodically. And in this specific application, one of the reasons that your model might get updated is people are going to change their data point based on the recommendation that you give them. So if a lot of them are going to kind of deploy what you told them, then you're going to have a different data distribution, which might require you to retrain the model. So if you retrain the model, this can cause the recourse that you generated with respect to your initial model to not be valid with respect to the updated model. So for the most part, I'm going to talk about how to handle this situation. So the most kind of basic way of modeling model change is to assume that your model class is parameterized by some parameter theta. So if you're using a generalized linear model, this theta can be the weight of your linear model. If you're using a neural network with a fixed architecture, these can be the weights of each of the layers. And to capture model change, if I have an initial model theta, and I have basically a knob of alpha of how much the model can change, I can look at the sum LP distance of theta and theta prime and use that to define similarity models with respect to theta. So this is a very powerful adversary that can change the model arbitrarily. But in practice, model change is less adversarial like this. I'm going to talk about some of those later on towards the end of the talk. So now if I consider this model change into the picture, remember before I had this term that was the cost of recourse. I had this term that was saying how far my recourse is from the desired label of 1. But that term was parameter, and that term had the initial model here. Now, I'm just going to guarantee no matter what model you pick from this set of nearby models to the original model, I want to have a recourse that minimizes this term in the worst case over all thetas. Yes?
Can you give some motivation kind of for like where this type of model change would like where you'd want to be robust, this type of model change? Is this just like someone's going in and messing with the weights, or is this like it's just purely adversarial, or do you have like another kind of setting?
Good. So I don't have a concrete example, but this is the easiest way to model something that can work even if somebody purely adversarial changed the model. When I'm going to evaluate this, I'm going to look at scenarios that how this model changes. But that's a great question. But I'm not going to think about how this model is going to change, because if I have some reason thinking about the model is going to get changed in a specific way, which I later on come and talk about, I don't really need to kind of go through this very restricted or stringent setting. So one observation here is in the easiest setting that your f is a linear function, your loss function L is a convex function, your cost function is a convex function. This is not going to be convex even in one dimension. And it has some connections to adversarial training that I'm going to talk about in the next slide. So how would generally people solve this problem? They solve this problem through basically similar ideas to adversarial training. So here is one of the first algorithms for robust algorithmic recourse, which came out in 2021, and it's called ROAR. So the idea is I'm going to have two players. I'm going to have a player who controls the x, and I'm going to have a player who controls the theta. So the player who is controlling x is just simply going to run gradient descent over x, assuming theta is fixed. But in each iteration of the gradient descent, the theta player is looking at the current x and kind of optimizes theta with respect to that. So this is a very timely procedure because we're running gradient descent, and in each round, we're solving another optimization problem. There are ways to speed up this thing in practice. You can restrict, instead of computing this theta prime exactly, you can restrict how many steps of gradient ascent you take. You can restrict how many steps of gradient descent you take. And you can kind of think about this as how much power you're giving to each of these players. So if you restrict the theta player, that means you're restricting the adversary to not be fully adversarial, but kind of make some moves toward the adversarial decision. And the same for the x player. So when it comes to empirical simulations, you see that this algorithm often does not converge, but for it to converge, you have to limit the power of adversary to something. So this may or may not converge, but if it converges, there is no guarantee of optimality because it only guarantees that it converges to a stable point. And there are many, many other algorithms that try to solve the exact problems with different loss and cost functions. So here, the only assumption was everything was differentiable. So I can do this gradient descent steps. And there's a nice survey last year that basically talks about all of these different works that try to solve this problem. Yes.
Do you have a good intuition about like that algorithm compared to just naively optimizing the theta, like how, and like if you weren't to do that maximization and then like were to look in the neighborhood afterwards, like post hoc, so you did it in 2 steps as opposed to like alternating the processes, like how much worse that would be, or is that just like catastrophically bad most of the time?
So I don't know the exact answer, but I wouldn't be surprised if you can make this very worse compared to what they're doing. But that's a great question. So there has been also a lot of empirical observation that if you want to empirically come up with recourses that have high validity, you have to increase the cost significantly, but we don't quite know how the optimal algorithm work. So the first question I want to think about is this high cost coming because we don't know how to compute the optimal algorithm? So I'm going to talk about a very simplified setting and talk about how to drive the optimal algorithm for that setting. And again, remember, this problem is non-convex. So even in this simplification, we're going to come up with an optimal algorithm for a non-convex problem. So I'm going to talk about, think about f theta being generalized linear model, like logistic regression. I'm going to define the neighborhood around the initial model with respect to L infinity norm. So that means each dimension of the model can change, but the amount of change in each dimension is bounded by alpha. And I'm going to talk about cost functions that is L1 distance. So I'm measuring how different 2 points are with respect to L1 distance. And each of these definitions have some limitations, each of these choices, but I'm going to come back and talk about those limitations later. So here is an optimal algorithm. So let me give you some intuition. If you have a linear model, essentially you're playing a 2-player game that the x player wants to maximize the dot product of x and theta. The theta player wants to minimize the dot product. So the algorithm does something very simple. The algorithm greedily updates x while making sure that theta prime is the worst response to x at every stage. So there are some challenges here because if you naively do this, it's not going to convert. So I give you one example. So suppose theta in one of the dimensions can change sign. So if you update x in that dimension so that x changes sign, the update of the theta is going to change sign, requiring x to change back sign. So kind of naively doing this will not converge. So we have an algorithm that I'm not going to go through the details, but kind of do this in a careful way. So the challenge here is even if you do it in a careful way, we're still doing best responses or kind of better responses in rounds. And it's known that if you have a non-convex problems and your players are best responding or better responding, this dynamic is not going to converge to an optimal point. It's going to converge to a locally optimal point, but it's not the globally optimal. So there is some kind of care and analysis figuring out what are some of the properties of the worst case theta prime and x prime, and kind of tracking the running of the algorithm to figure out some properties that the algorithm maintains through its running time to prove that this is optimal. The proof is not difficult, but it has a few pages of like carefully considering different cases. So just to say a little bit more about the algorithm, our algorithm is provably optimal, and its runtime is linear in the number of dimensions you have for your data points. And this F is basically the computational complexity of solving a one-dimensional convex problem. In our experiments, we can even solve this step by doing something like grid search, because we can easily restrict the search area in each dimension. So the runtime is pretty fast and experimentally much faster than ROR. So kind of like if you think about naively, what would be the running time of ROR? They're solving two optimization problems. In each step, you're solving another optimization problem, but those are in D dimension. So if this is like F1 running time of some convex problem in one dimension, they're doing FD, and they're doing FD squared. So roughly, if it converges, it's going to be much slower. And the other nice thing is empirically what we observe is when we're doing our algorithm, because we're greedily updating X, the solution we get at the end of the day is going to change only very few dimensions of the X. Whereas if you're taking a gradient step, you're going to basically change all of the features. So this has implications both for interpretability and kind of ease of implementation. So I told you about nonlinear linear models. So most of the things we have is nonlinear. So how does this apply? So one sort of crude up idea is if you have a nonlinear function, just approximate it with a linear function. So there are methods like Lime that are model agnostic, which means whatever model you give me, I can approximate it linearly. But the problem is that approximation can be bad. So I'm going to show you two sets of experiments. So again, remember, in our optimization problem, we had a term for cost, and we had a term that kind of corresponded to inverse of validity. So I can look at the trade-off of cost validity that I get for our algorithm. And remember, the algorithm had this knob of lambda that meant how much you care about each of these terms. And the smaller lambda means you care about cost less. So each of these are for a different lambda, and each point corresponds to bigger and bigger alpha radius. So as I increase the alpha, so this is the lowest alpha, this is the highest alpha, my validity decreases. So here you will see it. We compare this to ROR. So ROR finds solutions that have very low cost, but they're hardly ever valid. So the validity here is like around 5%. So that means your recourse is valid 5% of the time. While our algorithm, you can kind of decrease the lambda and get more and more validity. Here, I'm using lambda 0.1 for ROR, but even changing lambda to higher values don't really change the trade-off for ROR. So really, really matters that you're solving this problem optimally here. So this is the same data set, but now we're training a neural network model. And kind of you have essentially the same observation, but there is something surprising going on, because for neural network models, you're getting recourses that have high validity and also lower cost, which is exactly the opposite of what you expect. So sort of the problem here arises that if I have a linear model, I can compute the worst case model efficiently. So I have a more kind of a string baseline to compare with. Here, when I have a neural network model, I have to run gradient descent or something, and it's not going to converge. So the kind of, it's not an improvement in performance. It's just here, I can't really compute the adversarial data as efficiently as I can do here. So this is the same figure, but I added another approach. In red, it's kind of hard to read, but this is an approach that is designed to improve the performance of ROR for nonlinear models, because ROR also uses the same idea that if the model is not linear, just do a linear approximation. And again, here you see that one of our choices of lambda, so this is hyperparameter tuned for their approach, still it doesn't get a high worst case validity, but even for nonlinear models, like here is the case that their algorithm kind of work better for some regimes, but you see for the most part, our algorithm even performs comparably to the state of the art for nonlinear models. So now I'm going to talk about the learning augmented setting. So I'm going to use the learning augmented setting to reduce the total cost of recourse while kind of guaranteeing that the validity don't get hurt a lot. And Anastasios talks about this yesterday. So the idea is in a lot of problems, including the robust recourse that I talked about, we're going to assume no assumption on the data. Here, data was no assumption on the theta prime. So bad performance happened because some of these theta primes lead to some fragile cases that you need to handle with. So common approach in computer science to handle that is randomness. So instead of assuming your theta prime is selected adversarially, you're assuming there's some distribution over theta. So the learning augmented framework, or sometimes called learning with predictions, is trying to get beyond the worst case by assuming that you might be able to form some sort of prediction. So here, the prediction is going to be with respect to the worst case model that you're going to observe in the future. And the kind of idea behind this, as Anastasios was saying, is we have access to these machine learning models. We don't know that whether they give good estimates at all the times, but we expect as they're getting better and better, their estimates are getting better. So the learning framework, the learning augmented framework deal with the situation that you have access to some prediction. You don't know how good the prediction is, but you want to have this guarantee that if the prediction is accurate, you want your performance to be much better compared to the time that you didn't have the prediction. But if the prediction is arbitrarily bad, you don't want your performance to be much worse compared to the case that you didn't have the predictions. Because if you have a bad prediction, you can just ignore it, run your previous algorithm, and get some guarantees. So the fact that you're using the prediction should not make you to have much worse performance in the worst case. So let me give you one example. So this is binary search. So you have a sorted array, and here you're looking to find number 29. So if you're doing binary search, you look at the middle. It's less than 25, so you're going to restrict your search space to the right-hand side. Again, you're looking at the middle. It's more, so now you're searching, and you get here in 3 steps. But in general, the running time of binary search in the worst case is log n. So let's see what you can do with prediction. So here, prediction can be about many things, but in a specific point, I'm going to give you a prediction about where the index you're looking for is going to be. So here, the prediction says number 25 is index 4, which is wrong. So how can you use this prediction? So one idea is you can do something similar to binary search, but focus more on areas closer to predictions first. So the idea here is you start with the prediction index. If it was not the correct choice, and you need to go to the right, you go prediction index plus 2, prediction index plus 4. At some point, you're going to find a larger value, and then you're going to do binary search. So here, the prediction index is 4. That was not the number you were looking for. You're looking at the prediction index plus 2, and that's the index you are. But if prediction is more inaccurate, so here the prediction says index 1, it's not the correct answer. The next index you're searching is prediction plus 2, it's still not the answer. The next one is plus 4, and this is bigger than what you want. So now you're going to do binary search in this smaller neighborhood.
Just you're doubling every time.
Yes.
So okay.
So here, I'm not going to prove this, but the running time is order O of eta, where eta is how far the index that predictions say is from the actual index. So in the worst case, eta is going to be n. So this is basically optimal, order optimal, even if your prediction is arbitrarily inaccurate. I think binary search, you're just doing log n. Here, you're doing 2 log n. So the cost is a factor of 2, but in the order terms, it's exactly optimal, even if your prediction is wrong. So I was going to have another example. OK, let me talk about this first. So in learning augmented setting, you're looking at 2 measures of performance. One is called robustness. So this measures your performance when the predictions are inaccurate. And the other one is called consistency. So this measures performance when your predictions are accurate. Getting each of them by itself is easy. So in the first case, you just throw out the prediction. You get your robust answer. And in the second case, you just follow the prediction exactly, because this, and if the prediction is good, your performance is good. Because this measure of consistency only requires you to perform well if the prediction is correct. So each of them is easy to get by itself. Achieving both of them at the same time is not easy. So in the binary search, usually you look at this in competitive ratio. I'm not going to do that for simplicity, but your robustness is order log n, and your consistency is order 1. Because remember, if your predictions were accurate, the eta would be 0, log of 0 would be small. So, I was going to talk about another problem, which maybe I'll do it briefly. So this is an online problem that you're going to ski. You're a new skier. You don't know whether you want to buy or rent. You can rent with the price of $1, or you can buy with the price of B. You just don't know how many times you go. So the optimal strategy when you're not knowing anything about how many days you would go in the worst case is in the first B days, you rent. Once it comes day B plus 1, you buy. And if you go less than B times, you did the optimal thing because you just rented, you paid less than B. If you go exactly B plus 1 days, you paid 2B, B for the first days, B for the B plus 1 days. But the optimal would just rent every time. So your competitive ratio is 2. So this is a simple deterministic algorithm that gives you a competitive ratio of 2. So what do you do if you have a prediction? So here, prediction can be the number of days you go skiing. And D star is the optimal number that the actual number that you're going. So you have some function h that gives you a prediction. And you want to get some algorithm that performs well if this number is small, kind of gets back close to 2 if the number is large. I'm not going to talk about these algorithms, but I'll probably put this slide up so you can see that. So learning augmented has been applied to many settings. The examples we see are for online algorithm and data structures. It has been applied to mechanism design, privacy preserving. And even there is this website called Algorithms with Predictions that used to automatically crawl the web to find papers. But now it has gotten to the point that there are so many papers that you have to put in a request. So there are like already 250 papers from this field that has started in 2021. So learning augmented recourse, suppose somebody gave you a prediction of what the adversarial model is going to be. This is kind of a strong assumption. So usually learning augmented framework tells you somebody give you a prediction. It doesn't really tell you where you're getting the prediction. And this prediction can be arbitrarily inaccurate. I'm going to talk later about how we can actually form a prediction. So I'm going to define this J function. So this J function is exactly the cost of recourse that you have if your adversarial model was theta and the recourse you picked is x. So robustness just means the max of this J function when you can change theta. Consistency means what would be your J function if you had the model in prediction and you use recourse x. So our algorithm is actually pretty simple. So instead of doing the optimal trade-off, we're just going to look at what trade-off we would get if we optimize for something that is beta times the robustness cost plus 1 minus beta for consistency, and this beta is the knob of the algorithm. So again, in the interest of time, I'm not going to go through the details, but the algorithm we had for the robust recourse, we can just do some modification, and it also solves this convex combination. So here, you'll see with different predictions, you would get a different trade-off between your robustness and consistency. One thing that we see in our experiments is it is very easy in most of the cases, if your prediction kind of falls close to the optimal worst case model, that you can follow the prediction and not lose a whole lot on robustness, and vice versa. You can sacrifice a little bit on your consistency and get something that has a pretty decent robustness. So empirically, we can see how much trade-off we get between these two. One thing that kind of is analog to what will happen depending on how inaccurate your predictions are is something that is called the smoothness. So how does your prediction, how does your performance change as a function of prediction error? So we need to generate some predictions. So in a lot of data sets that has a temporal aspect, you can kind of use the data set at time t+1 to learn a model, and that model can be a prediction of what would be your future model. And then you can basically compare with that. Some of the data sets that you have data correction, you can take the corrected part and learn a prediction on that. And we also perturb this prediction to get predictions with different accuracies. So if you think about predictions as being the actual realized model tomorrow, you would get also some other models that might be inaccurate with respect to that. So here, I'm not going to go through a whole lot of details, but there are some funky things that are happening here. So sometimes you can do better if you are not using the correct prediction. So here, for each of these figures, I'm going to change beta and solve the optimization problem that was robustness plus consistency. But in each version, I'm going to use the different prediction. Some of the predictions correspond to the prediction that was the optimal prediction. Some of them are the predictions that that have some error, and measure the performance or baseline it against if I know the correct predictions. So these things are not only non-monotone. There are some regions that you would get lower loss compared to the following the actual prediction. So I'm not going to talk about this because I want to talk about some future directions. So this model of adversary was very strong. In practice, a more sensible choice for the adversary would be to model it with L1. And even in some of the cases, like if you have a neural network, you don't want to change the weights of all of the neurons. And people studied weaker notions like, it's called, I forgot what was the exact name that they had. For the neural network, they studied weaker notions. So I think it would be interesting to revisit this problem with those weaker notions or L1 distance for the model change and see whether we can get theoretical guarantees. And we don't have any theoretical guarantee about the relationship between robustness and consistency. We just have some experiments. It would be nice to get some theoretical guarantees. But I want to talk about a couple of alternative directions about both robust recourse and algorithmic recourse in general. So one idea is if you were going to do robust recourse because you were worried that once people move based on the recourse recommendation that you gave them, the robust recourse in some sense is overkill. So if you were worried that your model is changing based on your distribution changes that you recommend, you can try to model that directly. So this kind of comes back to the problem of algorithmic recourse, that you're giving recourse to every individual separately, but you don't really care about how this is going to affect the population level. So we call this performative algorithmic recourse because this is sort of, for people who are familiar, this is the exact framework of performative prediction, that the model you're going to deploy is going to change the distribution of data in the next round, and you're going to try to find stable point. So that means that the model that you're going to use, if people move with respect to that model, the model you're getting tomorrow is exactly what you propose. So this is one direction. The other direction is algorithmic recourse talks about the situation that you want to find a point that the label of the classifier is 1, but that might not be what the decision maker wants. So for example, if you're a bank, you don't really care if somebody that you're giving recourse passed your classifier tomorrow. You actually care about them paying back the loan. But the problem is you don't really know what the true label is going to be. You know what your classifier is going to predict, and these two things might be different. So in general, you don't expect that you can estimate the ground truth with any level of accuracy. So you want to basically distinguish between two cases that we call gaming and improvement. So improvement, consider the cases that what you suggest both pass the classifier and result in the true ground truth label of 1. Gaming is you just pass the classifier, but you haven't really improved, so your true label is still going to be 0. So this requires some knowledge of the causal relationship between the features and the true labels. And you basically want to pick your classifier that incentivizes changing the true label in the direction you want. So this will result in a bi-level optimization, generally non-convex. We can find some approximate solution, but the error guarantee is not very well. This is a work in progress. I would be happy to tell you more. And I'm going to conclude with 2 other open questions that people don't consider when they're looking at the recourse formulation. So one is fairness. So essentially, one problem with the whole algorithmic recourse literature is, as I said, you're giving recourse at the individual level. You don't look at the population effect. So fairness becomes very important here because whatever you're going to recommend might change the distribution of different protected groups that you have in different ways. So you want to care about how to model that. There is not a whole lot of work thinking about this problem. And the other problem is, in practice, you might want to compute recourses with respect to multiple functions that you don't know. And I give you a few examples. So you're going to optimize for chance of yourself of getting to a college next year. You have a bunch of colleges that might have different criteria, but you don't even know what are these functions look like. Maybe you can look at your high school's previous years and see who get in or who didn't get in to form a prediction about what does these models look like. But you want to optimize kind of jointly with respect to all of these models. So you don't want to kind of come up with a recourse that is valid with respect to each and every one of them. That would be an overkill. So how would you model situations like this? So I think this is a good point to stop if there are questions.
Thank you. Round of applause. Yeah, so we should have time for 1 or 2 questions before we close out. Anybody has one, or I can start the discussion. Oh, yes.
I actually wanted also suggest maybe a different approach for recourse. This is actually very interesting because that is also what I am considering. How would you, if something does not hold, would you explain what you need to change? But I was actually considering from a different approach, and maybe you already have some experience I would like to hear, was the following. If something does not hold, so thing as it is unsatisfiable, but now what Subraktik told us about max set. So you would kind of say, okay, identify me what is satisfiable, and now what can I change in this unsatisfiable part? Did you consider anything in that direction or not?
No, I think kind of figuring out what is satisfiable here is not trivial. So that's a very nice suggestion. I haven't seen any formulation that kind of looks at it that way.
Okay, thank you.
Any other questions? I have one actually about that dip that you showed when you have the wrong answer. I was wondering if you had any intuition about, like, so binary search itself, right? Is if you naively take it as thinking of it as guessing the next answer, and it goes to the middle. In some sense, it's like an information gain question. It knows it can at least throw out half of the solution space. And I'm wondering if it's a similar phenomenon that's happening there with that dip, where by being wrong, it's okay because in some sense you're restricting the solution space more.
That's a good observation. I think the kind of problem comes with this sort of algorithmic approach we are taking. So it's unclear the best way of incorporating prediction is to solve for a convex combination of robustness and consistency. So I think it's more coming from the choice that this algorithmic choice is somewhat hard to justify theoretically. But the intuition that you have is correct.
All right, thank you. With that, let's do one more round of applause. Speaker. And then, so Sanjit has asked me to give some closing remarks on the session. I just want to thank everybody for coming. I think, this has been very informative. I've heard the hallway track, a lot of productive discussions, and I think ultimately that's usually where the long-lasting impacts of these kind of workshops happen. And so I think this has been, amazing, and I'm hoping that people keep in contact and make sure to kind of keep this research going. And by probably next year or so, we'll have trustworthy AI figured out, right? All right. Well, thank you again to everybody, and yeah, feel free to reach out if there's any last questions. And thanks again for the Simons Institute and yeah, all the other organizers who aren't currently here. So.